Hello. So, let us resume our discussion on flow networks today. First, I am going to just review the main results of the last lecture. Recall that a flow network is a 4-tuple. The first one is a complete directed graph, a capacity function, a source vertex and a sink vertex. So, let us first define a star property a set E prime of the edges has this property if every path from S to T. Now, naturally we are talking about directed paths. From S to T passes through at least one edge of E prime. Okay. So, if E prime satisfies this condition, we say it has star property. Then just let me review the results. One was that E prime, which is subset of V cross V, is a cut set, is a cut set or the edge set of a cut set if and only if E prime has star property and 2, no proper subset of E prime has star property. Last time what we mentioned, the same thing was mentioned as E prime is the minimal set having star property. The second result that we had shown in the last lecture was that for any cut S comma B minus S, the cut capacity is greater than equal to flow from S to B minus S, which is equal to the magnitude of the flow. And we had stated our main problem. Our problem was to compute a flow for a given flow network flow F such that this is maximum. Now, in order to compute such a flow, what we need is to characterize what property of flow which is decidable in a local computation says that the F is maximum. So, we will state a very well known result in this domain which says the following, which says that if F is a max flow which means that mod of f is maximum possible flow. So, if f is a max flow for a given network, then the value of the flow is equal to the smallest cut capacity. So, over all the cuts S comma V minus S, the capacity of that cut. Here what we have noticed is that the magnitude of any flow is less than equal to capacity of any cut, and this theorem says that if the flow is maximum, then this will be equal to the smallest cut capacity. So, let us try to prove this. Suppose f is a max flow. So, this f is one of the possible flows where the magnitude is maximum. Now, what we will do is we will define a set. Let E prime be the set of edges x comma y such that x comma y is saturated in F. Now, recall that by saturated we meant that the flow in this edge, that is f x y, is equal to the capacity of this edge C x y, or equivalently the residual capacity of this edge for this flow is 0. So, I have collected every single edge which is saturated in this set E prime. And now, first claim I am making is that E prime has star property. Star property is that every path from S to T must pass through some E prime edge. Now, to prove the claim, suppose we assume the contrary. Let us say there is a path which does not pass through any of the E prime edge. So, suppose P equal to S x1, x2, xk t be a path with none of the E prime edges on it. In that case, edge Sx1 must have flow strictly less than the capacity Sx1. Similarly, the flow on x1, x2 must be strictly less than the capacity of x1, x2, and so on. So, every edge on P has positive residual capacity. Positive residual capacity is the capacity minus the flow, and since none of them are equal, they are all going to be positive differences. Okay. let x be equal to the minimum of all these residual capacities. So, let us just say minimum of, we denote residual capacity as Cf of S x1 comma Cf of x1 x2 now you can visualize this as, here is S, we have x1 x2 x3 and so on, finally it reaches T. This is xk, maybe we should use some other symbol for this. Let us say this is some alpha. Now, suppose we add the flow, so we define new flow on this as f of S x1 plus alpha. Similarly, here S x1 x2 plus alpha, and similarly original flow xk t plus alpha. In the rest of the graph, we leave the flow intact, we do not change anything. So, the first question is that the new flow that we have defined, let us say the new flow is denoted by f prime. This is a function assigning values on each of the edges. Is this a valid flow? So, notice that in any edge other than these paths, the flow remains intact. If the two end vertices of this edge are different from these, then the Kirchhoff's law on these vertices remains valid, because we are not changing any of the flow going into it or leaving it. The capacity constraint, namely the flow should not exceed the capacity, is also unaffected. Now, let us talk about these. This edge had capacity C S x1, C S x1, flow was S x1, and the difference was greater than equal to alpha. That was the choice, alpha was the smallest of these. This is our Cf of S x1. So, when we append the flow, we have C S comma x1 minus f prime of S x1, which is equal to C S x1 minus, now f prime is f of S x1 plus alpha, which is C S comma x1 minus f of S comma x1 minus alpha. From this inequality, this is still non-negative. Hence, we do not violate the capacity condition on this edge, and the same goes for every one of these edges. So, we are not violating any of that. Now, as far as the Kirchhoff's law, the law of conservation of the fluid is concerned, at this vertex, the earlier sum was 0, whatever was entering was leaving, and now we have added alpha entering and added alpha leaving. So, once again the net flow at each of these vertices is 0. It certainly is more for this and more for this. So, what we notice is first we observe is that f prime is indeed a flow, a valid flow. And second observation we have made is that the magnitude of this flow is, the reason is we had shown that this is equal to the net flow emerging from the start vertex. The only thing that has changed from f to f prime is that now added alpha flow emerges along this edge. Hence, we have mod f plus alpha, which is strictly greater than f. What we have found is that we managed to improve the flow, which should be absurd. Why? Because we chose f to be one of those maximum flows. Nothing should improve upon this. Hence, we have established that E prime has star property. Okay. So, E prime has star property. Now, let E double prime be a minimal subset of E prime. So, I am picking some subset of E prime which is as small as possible and having star property. So, I still want this to have this property. Well, certainly E double prime exists, because if every subset of E prime fails to have star property, then E double prime will be E prime. So, there is no problem in establishing the existence of E double prime. Now, we have shown that whenever a set of edges has this minimal set, E double prime has star property, it is actually the edge set of a cut set. So, from our earlier result, there exists a cut S comma V minus S such that E double prime is the edge set of this cut. Okay. So, now we know a set of edges which is the cut set, which is the edge set of a cut, and what is more is that each edge of E double prime is saturated, because that is how we had constructed E prime, and E double prime is its subset. So, now what we have is, we got to now show that the capacity of this cut matches with the magnitude of the flow f. So, now we will take the cut that we just figured out, and we know that its edge set is E double prime, and every edge in E double prime is saturated. Then let us ask, what is the capacity of this particular cut? So, the C of S comma V minus S is some C of x comma y, where x comma y belongs to E double prime, the edge set of this cut. Since every one of these edges is saturated, then the flow through these edges is equal to the capacity. So, we can also say that this is equal to f of x comma y for every edge in E double prime. This, from our result that we mentioned at the start, is equal to f. So, what we have found is that the max flow is equal to the capacity of this particular cut. Now, we had earlier seen that C of S prime comma V minus S prime is greater than equal to F for all cuts. Hence, this has to be the minimum of all the cuts, and that establishes our theorem that if F is a max flow, then the magnitude of that flow is equal to the smallest cut capacity. This hints towards the fact that where up to what point we can actually go. This tells us that as long as there is no cut which matches, whose capacity matches with F, there is room for improvement in the flow. We can always increase the flow. Now, in order to develop an algorithm to compute max flow, I will need to define something called a residual graph. So, in our network graph, we have say V set of vertices, these are the vertices. Then I am going to put an edge, a directed edge in the residual graph. I will call it G F. If the residual capacity of this edge in the flow is positive, that is, if Cf of x comma y is strictly positive, and we will not put any of the edges in this graph where the residual capacity is 0. All the edges which are saturated are dropped from this graph. And now we have built a graph based on the given network and the given flow F. Now, what is the property of this graph? So, we have some S and we have some T in this. Suppose there is a path from S to T in this graph. Let us suppose we have a path like this. Then on this path there is a minimum positive capacity, residual capacity, because there is some positive residual capacity alpha 1, alpha 2, alpha 3, and say alpha is the minimum of all those capacities. Then, as we have seen in the proof, what we can do is that we compute alpha, and in the original flow we append that much flow alpha along these edges. And if we do that, we have seen that our net flow will improve by alpha amount. Hence, the problem of finding such a path with positive residual capacity is same as finding a path in residual graph. That is the purpose of defining this graph. So, now we have a theorem says that a flow F is maximum if and only if the residual graph has no path from S to T. We just saw that in case there is a path, then I can always improve the flow, I can increase the flow. So, it is clear that if there is a path, then F is not maximum. So, this implication is trivial. So, let us try to prove the converse. This time I want to show that if indeed F is not a maximum flow, then there always exists a path from S to T in the residual graph. Okay. So, let F be a max flow, sorry, a non-max flow, because we want to show that there will be a path in this case in the residual graph. So, how do we proceed? Let us start with a set S naught equal to just vertex S. I have just the vertex S in this set. Then we can define a cut S naught comma V minus S naught. This is a cut. In our previous theorem, what we have seen is that the maximum flow meets the minimum cut capacity. Since F is not maximum, the cut capacity of this cut has to be strictly greater than the value of the flow. So, the capacity C of S naught comma V minus S naught has to be strictly larger than the value of the flow. This comes from our previous theorem. What does that mean? It implies that there is at least one edge in the edge set of the cut which is not saturated. There has to be some edge. So, here is our set containing a single vertex. This is set S naught. The edges are like these, and there is one such edge which is not saturated. Let us call that SY1. Okay. So, there exists edge SY1 such that capacity of SY1 is strictly larger than flow on it. In other words, the residual capacity, the CF of the edge SY1 is positive. Now, let us go and define set S1 as S comma Y1. Define the cut to be S1 V minus S1. Once again, I am claiming the capacity of S1 comma V minus S1 is strictly greater than the flow, and hence, so again there exists an edge in the edge set of S1 comma V minus S1 with which is not saturated. So now you have set S1 containing two vertices S and Y1. So there are edges coming out of these, and at least one of these is not saturated. Now that edge may be SY2 or Y1 Y2, it does not matter where it emerges from, but say it ends up in some vertex Y2. Then let us say, suppose that edge is SY2 or Y1 Y2. Then this edge has positive, this edge also has positive residual capacity. What is more, I also know there exists a path from S to Y2 of edges with positive residual capacity. Well, in case the edge was SY2, then that is the path. You have a path from S to Y2, and since it is the only edge, we already know that its residual capacity is positive. On the other hand, suppose the edge was Y1 Y2, then the path is the edge that we had picked up earlier was SY1 followed by Y1 Y2. Both of them had positive residual capacity. So now we still satisfy this requirement of existence of a path from S to Y2. Now once again we proceed in this fashion. Now we take S2 to be S comma Y1 comma Y2 and define a cut to be S2 comma V minus S2. Now what has happened? Once again we will argue that our capacity of this cut is strictly greater than the flow, and hence again there is a edge from this set to somewhere out to some Y3, and the residual capacity is positive. Once again I will be able to argue that there is a path from S to Y3 with each edge having positive residual capacity, because if it starts from S, then that is the edge. If it starts from Y1, then the path will be SY1 edge, which has positive capacity, residual capacity. Y1 Y3 has positive. And similarly, if it starts, if the edge is Y2 Y3, then SY1 followed by Y1 Y2, if that was the previous path, followed by Y2 Y3, or SY2, if that was the previous edge, then SY2 followed by Y2 Y3. In all situations, I will have a path with positive residual capacities on its edges from S to the latest vertex. This process will continue. Finally, at some stage, some yi will be t, because we have a finite graph, at some point t must enter, and once that happens, we have shown that there is a path from S to t on which every edge has positive residual capacity. That establishes our second part of the claim. So now our result leads to an algorithm which is known as Ford-Fulkerson algorithm. To be precise, this is actually not an algorithm but more like a method, because it lacks one important property of an algorithm, which we will see. What this says is that let us initialize a zero flow in the graph. So, set f x comma y to be 0 for all edges x y. So, note that this is a valid flow, it satisfies all the conditions of the flow required. Then compute the residual graph. Note that all this is in this case is doing is dropping all the edges with 0 capacity. Now, then while there exists a path from S to T in H, do compute a path P in H from S to T compute alpha equal to the minimum of all the edges in P, the residual capacity of E. So, all the edges on this path have residual capacity alpha or more. Append f by adding alpha flow on P. Leave all the other edges intact, but all the edges of P now will have alpha more flow. And when this thing is over, you return f. Well, if this is over, that means there is no path in the residual graph. Okay, to be precise, I should say compute residual graph. Compute residual graph, and that would be it. So, if we come out of this loop, then we know that the residual graph has no path from S to T, and then this theorem tells me that this flow has to be maximum. So, if this correctly returns a max flow. The problem why I am not going to call this as an algorithm is that there is no guarantee that this process will terminate. It may go on forever. Although you can notice that if all the capacities were integral, suppose all the capacities are integers, then each increment will be at least of 1 unit, and the minimum capacity, cut capacity is say capital C, then you will need at most capital C iterations. In that case, it will terminate. In fact, you can argue the same even when the capacities are rational. But if it is a general real number, then we may not be able to argue that this will terminate. Now, let me run a small example through this. Let us take let us suppose we have a network. Remember, I will not show in our representation, I will not show edges with 0 capacity for convenience. Initially, I will have 0 flow in this, all the edges. This is the initial stage. Notice that the residual graph is exactly this. So, I pick a path. Suppose I take a path, namely this. The residual capacity here is 10, it is 3 here. So, the smallest number is 3, and I will append that much flow. So, I will make this 3 and this 3. This is a saturated edge. So, I am going to remove this edge. The broken edge is the missing edge from the residual graph of the new flow, and the residual capacity for this is now 7, because we have 10 capacity and 3 is flowing through it. Others are intact. Once again, I will look for a path. This time, say I choose this path, and I find that the residual capacity here is 4 and here it is 5, minimum is 4. So, let us append that flow. We put 4 here, we put 4 here, and once again this is saturated. So, I will drop this from our residual graph and just leave it as a dotted line, where the 4 denotes the original capacity. Still there is a path which goes like this, this and this. Here the residual capacity is 1, it is 7 here. This has 5. So, we have 1, 5 and 7, the minimum being 1. I can append 1 here. So, this time this will become 4, this will become 1, and this will become 5. Now, the residual capacity is 0. This is a saturated edge. So, I am going to drop this edge as well. And now, this is one of the edges which had 5 capacity. So, the flow that we have computed of course, the capacity is being 10, 3, 5, 4, 5 here and 7 here. We are putting 4 units here and 4 units over here, 1 unit into this, 5 here because this was saturated, 3 here and 0 here. So, what we have shown is that such a flow where the residual graph has no path left has to be maximum, and notice that the value of this flow is the sum of the fluid coming out of the source or what enters into the sink, which is 8. This is the maximum flow for this network. So, now to be able to give a proper algorithm, we need a way to ensure that this process terminates, and this is what we will do in the next lecture. We will offer an adaptation of this method, and that is called Edmund-Karp algorithm, which suitably tells how to compute the path such that this loop terminates, and that will be our next topic.